Okay, how is everyone doing? So sorry about the delay, but I think we are now live and ready to go. Let me hide that. Let me switch up my docs and things. Okay, that should be good. Okay, I'm gonna get rid of that banner. Okay, cool. So we're live now and ready to do our first kind of low level stream. So like I kind of mentioned before, there'd be like these high level streams and the low level streams. And since Tuesday is like kind of really early for the US, I thought that the low level streams would be best to happen at this time. But I do have other meetings and stuff like that, which push this back, and got to probably do something about that so that we can start at a proper time. Maybe I'll push this stream to start at like 11 p.m. my time instead of 10, so that I don't have to like, make everybody wait, But anyway, so the plan for today is to take Llama 2C, which is a Llama implementation that Carpathy has made, and try to get that running on the vector engine. Now, I know it works on the vector engine. It works just fine. And mainly we're interested in the inference, not so much the training. And yeah, so a couple of things I want to do today. So I do know that it runs, but it's, we're running on a little maybe old version. And there's now possibly a more newer version here, which I might need to update. And so we'll do that, get it up to date. And if I'm not mistaken, in the latest version, you can also run the, like Llama 7B models with, like this. You can convert the model into the binary that's needed and then run that. We'll see what we can get in terms of performance on this. The code is originally made for single thread, and I think it now has OpenMP support, which is good because I also added OpenMP support in my other branch. And yeah, we'll see. So this will be just a lot of C++ and stuff like that, and figuring out how this works. And ideally, once we get this working on the vector engine, what I wanted to do was add that into our XAI LLM server so that we could have a, Llama 2 7B option in the LLM server here. And then we can use that for Technologic and things like that. So, let's get started. So first, like as a baseline, I think I'll run. So here I can run make. You can see it's using GCC 3, and that's okay. But if I do that's math, hyphen in between, yes. Yeah. And then run that, we get double the tokens per second, 104. And that's, that is pretty good. The run that I have before here can get more than that. but the calculation's a little weird. It's weird because the way they're using to calculate time is a little off, a little weird. So got to do something else. Oh, interesting. So that seg faulted. I'm not 100% sure why. The name wouldn't matter. It was running a couple of minutes ago. I thought it was all self-contained in this run, but I guess I could be wrong. Anyway, so let's go through the simple things. So to get this to run on the vector engine, so let's first look at run.c, see what the latest versions of it is. So they seem to have added Windows support, which is interesting. I think they are now using time instead of the other thing, so now they'll get proper timings, and there's a lot of kind of callocs at the beginning, I think, which is good. These are all things that will make things a little bit faster. Okay, cool. And they're also using OMP, so we can leverage that. And yeah, so let's see. So let's first check out our VE changes. So here's kind of old, but in here there's this compile.sh that I want. Check out master. Why is there? Let's go get checkout main. Okay, so there's no upstream main. What? So does master be upstream? I see, it is. Okay, and then there's like a difference between the two things. So let's get branch M, which I think change my master, and get checkout. So let me get branch D master. And git fetch. So let's just get everything into our Git repository and then git checkout master. Okay, so now we should have the latest and greatest. We'll make clean to get rid of everything. Okay, there's a few more lines of code now than there used to be, which is good. Well, makes our lives a little bit more complicated. Whatever. So first, let's make, we should have our run.c. And kind of works. Now let's create here a new file. Compile sh. And yeah, so here we can switch between the different things. So if I do sh compile.sh and now run this, 80 tokens per second, not so bad. I have the feeling the OpenMP is not really helping too much. Let's just compile and see what we get with the VE. I need to source the NLC vars. May or may not help. H. We have, okay, so this is the M parallel version. It has inlined matmul, but that's not generating the matmul thing. That's not going to work so well. But we can still give it a try. So if we run this, get 94 tokens per second, which is, better. But I think we can do better, or we might be able to do better. Let's get rid of M parallel here. And do F open MP. And try not to forget our backslash. Okay, now let's run this and see what we get. 91. That was slightly less than before. And still kind of not great. Okay, so the main things when it comes to NCC, and I am running maybe a slightly older version of this. A parallel routine generated for matmul. We've inlined and vectorized all these things. Okay, but for me, the main thing is the matmul. There's a special directive in the compiler to detect matmul, essentially. And I kind of have to remember what it is. It'll be a little difficult. Yeah, I think, okay, let's go back here. Let's get rid of this version and instead allow us to play around with parallel and fopenmp. And then we'll just put false here. And then compile sh. Let's run that. I have 91 tokens per second, which is okay. Not great, but okay. And let me see if there was a manual page on it. Let's see, pattern detected. So I think I have to do to generate the right code is to write Fortran in C, essentially. And I think I've done this before, but the code for it is now long gone. But I'm pretty sure, or is it long gone? It might not be long gone. It may be in the Spark Cyclone ML. I have the feeling it would be in here somewhere. But I could be wrong. Yeah, it could be wrong. But anyway, I'm pretty sure I kind of looked at this manual and got it. And essentially, the Fortran kind of has fixed size arrays, and we should, and if you add those same kind of annotations to your C declaration, then it will also kind of realize, oh, this is a matrix multiply, and will generate better code. So let's look in here and see how this works. Yeah, the other thing that I have my eye on is this, which you may or may not do, but it's like a Fortran version of RWKV, and I do kind of want to see how that performs. So we might look into that as a bonus thing if we get to it. Let's see if there's mul. No, there's not GMML. There's not any mention of that here either. And now I really wish I had that code lying around somewhere. Anyway, the way this needs to work is that we need to change these to arrays. And we want to give them dimensions. So this should be D. It should be M. to find. Something this simple, isn't it? No, it is something that simple. Okay, so we have our N and D. We have these set up. Then the problem is every time we call mapmul, the last two dimensions need to go to the front. So I think we can figure out how to do that in VS Code, or we select a rectangle. Or just add dim to the first parts everywhere. So let's do that. And get rid of these. Okay, same thing here. One, dim. These. Dim, and then get rid of, ooh, and then this is dim and hidden dim. And this one is hidden dim. There. Then here we should have here. Okay, let's see if that compiles. Okay, so we have warnings and an error. This version must have an arithmetic type. So this does not have an arithmetic type. Though at the same time, I'm kind of like wondering, is it worth doing this or just replacing this with a call to something else? Might be worth doing that. Man, where did I so remember spending a lot of time optimizing mapmul, but I cannot recall where I implemented it. It has to be here somewhere. On GPT-2. Fast GPT. This one can't be this because this is Fortran. We might start thinking about implementing things in Fortran. Okay, so it's not fast GPT, but it could be like nano GPT. It's not nano GPT. Oh, it's so annoying. I totally remember doing this before. Oh, so annoying. Couldn't be in research. Oh, we didn't do anything in C++ there. And not that. Galactica. Okay. Okay. Yeah, parallel. That is missing a lot. Where did I do this before? It's really annoying me right now because I'm totally remember doing it, you know. But we'll have to see. Anyway, so let's see. Okay, so we have ND, X out D, and this is saying that this needs to be an arithmetic expression, which it is not. And that is because it might look like that. Okay, then we can try that again. Okay. Now we have our incompatible floats and things like that. That's kind of fine. Parallel routine generated for matmul. Let's see if this has the same results. Should. Oh, it does not. It definitely does not. We have totally messed it up. I times n. Don't need n. Closer. W has 2 dimensions. I is up to D, so that is correct. And then this is up to N. That is correct. Up to D. Previously. A times n plus j. Did C allow us to do that? It does. Okay. A little bit better. Okay, let's get rid of the parallel stuff real quick. Save there for laziness. Yeah, that's a good idea. Let me just check real quick what the single is 74 tokens per second. So you're gonna vectorize loop, inline matmul, that's not ideal. And that's pretty much it. Okay, so we are at 73 tokens per second without that. Okay, let's try turning on OpenMP and we want X out as shared. Routine generated matmul. And that's 90. You were getting 93 before. Yeah, 93.9. Now we got 90. And I think that does come down to like M parallel generates a couple more things. Can we do parallel? Parallelization sometimes works. That 91 could be in the margin of error. No, it's not, but it's it's a little bit better. That's in the margin of error of not doing it. Okay, so there's that. Okay. Matmul is not detecting as a pattern. We want it to detect as a pattern. So let's see. NEC, NCC, pattern detected. How can we get those things? What was it, man? So annoying. I don't think they had it in VEDNN either. I'm pretty sure they use a different matmul. We could also just implement. See, the VEDNN have a matmul. So the VE is the VE. It's a good question. So thanks for the question. So this is the NEC vector engine. If we look at the wiki chip, and I hate looking at chips sometimes. Let's look at as the advertising. We can see the special architecture that is the vector engine. So it is a vector processor, and we want the SX Aurora microarchitecture. So architecture. Yeah, that's good. And essentially the kind of special sauce about the whole thing is that it has this vector processing unit where it can do essentially 256 operations in a single instruction. It takes about 2 or 3 cycles, or yeah, 2, 3, 4 cycles to do that, depending on what you want to do. And be pretty interesting. In general, the way you program things with the VPU is to just kind of create loops. And if your loop is simple enough, it will get vectorized. So you can see these vectorized loop outputs from a thing. You can also look at the compiler output. If we didn't set it in the mode, you can have a you can specify, you can see what it's vectorized and stuff. And you're right, it does have a low level matmul, so we can use the big GMMMs, and we should be able to do that. I want to try that as well, but we can also there is a way to specify matmul in a way like this, where it generates a specific pattern, right? So like the NCC has some patterns. One of them is sum, average, and things like that. And if you write those things in the right way, it will mention that it's detected that pattern and has generated that routine for you in essentially like the most optimized way it can be. Yeah, and the compiler, the NCC compiler, is specific for the vector engine. So we just use that. We tell it 04 when we want it to be serious about the performance, and that should kind of get us most of the way there. And then the other thing is the vector engine has eight of these, right? Kind of organized in a little bit of a ring buffer. And you want to use either OpenMP or NEC's like parallel routines to leverage all 8 of those cores at the same time. Each one has this 2 megabyte last level L1 cache. The bandwidth between this cache and the core is quite good. And then the bandwidth from in total of all the cores to the HBM2 memory is about 1.5 terabytes per second. So pretty good in terms of that. And I think this is 3 terabytes per second, like from here to here. So you can get pretty good performance if you get it, doing the right stuff. And the NCC compiler, it's really made for Fortran, or as in it's way better at Fortran than it is at C. And one of the things, I'm not sure if we'd have time for it in this stream, but one of the things that we could probably do to make it work much better is to transpose the weights so that they're in the other direction. And that will work so much faster. We can actually see what's going on if we do VE prog inf equals detail. After the program runs, we can see the kind of real-time vector instruction time, how many vector instructions there were, the flops that we got, the average vector length, which is 160, and the vector op ratio, which is 40. So what this tells us is that when this application was running, 40% of the time was scalar operations, which is not what we want. So the SPU is an out of order superscalar kind of CPU. right? So that it's not bad, but it's also running at 1.8 gigahertz, which kind of sucks, right? Like it will get you more or less what you expect an Intel CPU running at 1 point something gigahertz to do. But if you really want the speed, you want it to be using vector operations, right? These run, you get 256 times 8, so it's like having an AVX 2K, right? Yeah, so it's 2048 times 64, right? So it's like a ridiculous number. It's like AVX 128,000. So when you get that working, that works great. So there's room to improve. Essentially, like we're kind of using 40% of the core's performance, and we are wasting instructions. We should be able to pack more than 160 elements. We should pack 255, 256 in here for every instruction. So yeah, this just tells us that there's definitely more that we can do. And we can totally use OpenMP for doing the multi-core thing. So this works, right? So if we just have that, we add the fopenmp into the compile, it will use OpenMP. Okay, so I want to recall the pattern detected stuff. Let me see. Because there was a few. Yeah, the performance tuning guide. I have this one already. Let's see some. Max. Yeah. So one interesting thing that I've kind of discovered when it comes to like unrolling this, you totally can, but I haven't particularly seen it work better in general. So yeah, hold on. Let me see if I can find. I'm pretty sure what I'm looking for is that top K thing. Because when I was working on top K, so essentially what I was doing with this whole top K business was creating a vector engine specific top K implementation, which we would then use in our vector database. And that was very fast. It was also, not exact. So I was able to kind of have this 256 element sliding window for the max. So as long as your K for your top K was less than 256, there was a good chance that it gave you the real top Ks. And we'll look at this a little bit here and see if C-Line can get its act together. Come on. I believe in you, C-Line. You can render this, render whatever this page is. So yeah, like my experience with doing this was like, you just have to do a lot of experimentation. The specifying specifically that this is 256 elements and this is a max. It doesn't work, like you can't beat the compiler in general. By like giving it specifically a loop that's exactly 256 elements, and kind of, you can kind of imagine what the vector instructions will be. That didn't work very well, but making a genuine kind of like, here's a 256 element array, then you fill it with stuff, and then you have this, for loop of 0 to 256, and have, something simple like that. That can work, right? So if you do like special 256 element buffered versions of things, then you're cooking with gas. It's very different. I think it's this importing that's a problem, and this project is not made to be run locally, it's made to be run remote. So we're going to have to wait a little bit more. Now, the other thing that we can do is use, and I don't have a lot of, I don't have a ton of confidence in this, but we can try it. So there's this thing called the NLC library, which should be good, as you would expect, because it has CBLAS. And this has the CBLAS GMMs. And I think we want that one. Right. Pretty sure that's the one we want. So let's figure out what we need to do in our C code. So I think we want to add include CBLAS-H. And then in our matmul, let's make this be original matmul. Then I'll create another matmul that is just a wrapper for the CBLAS SGMM. I can remember what the SGMM parameters are in their order. Oh yeah, I was using CL Blast the other day for like Llama, like using it with llama2.cpp. SGMM, yes. Okay, now the problem with this is that it's a little bit more involved, and I'm not sure. I'm going to assume that these are not transposed or anything like that. And that we don't need to transpose anything. Could be wrong. Be very, very wrong. Okay, and then let's look at logpack. And we want, because we're dealing with floats, right? So we want reals. And these are not symmetric matrices. This is a matrix, and these are vectors, right? So what we want is this operation is a What's the word that I'm looking for? Computational routines in real. This is a matrix multiplication. It's what's it called? It's like a matrix vector multiplication. Though it could, a vector is just a one matrix with the dimension 1. So I think it might be able to work. Let me see if I can search. Anyway, so these transpose has to be n. Okay, we want C class SGMMM. We want n. Rows of the matrix A. So this is going to multiply A, B, and plus C alpha. So it is a mx plus B deal. And or no, this C is the output. Yes, it's the output. Okay, that makes sense. So we'll want A is going to be W. The length of A is B. Then B oh wait, I forgot M, and K. We have M, N, this M, then K, then we want W, E, and then we want X, which might be 1. Yeah, and then X out. Then M is the length, number of rows of A and of matrix C. So M should be B. N is the number of columns of the matrix B, which should be this. And that is 1. There's 1 column. And K is the number of columns. And is this 1 or is this n? It's a vector. And is a vector a 1? Yeah, it's a 1 by n, essentially. Right? That's what we want. It's a 1 times n. And this is a b times 1. let's compile and see if it's too few arguments. Did I forget something? Ah, yes, we have alpha. This is plus, or no, it is multiplied by alpha. Alpha is multiplied by that. So f before w, we'll want 1.0 f alpha. What more do you want from me? We have a, b, m, n, k, the alpha, matrix A, which is w, the rows of A, which I'm guessing is D, given that. Then X, which is a vector, so it should be 1. Then a real beta. Ah, okay, we're missing the beta. The beta is multiplied by C. Okay. C is in out. Beta specifies the scalar when beta is applied as 0, then C need not be set on input. Not A. C. If C is 0, then that would be multiplied by 0. And C is, oh, it's both an input and an output. Before entry, the leading m by n part of array C must contain the matrix C, except when beta is 0, in which case C need not be set on an entry. So I think I want the beta to be 0. So that way it's not, we don't want it to use this at all, right? So saying 0 means we don't set it. Gotta love Fortran. Okay, and we have C and LBC. And we are missing this time. I wish I had like proper A to E so I can look at what the C plus H specifies. So I'm looking at the right thing. So we have order, transpose, float beta. Are we missing the order? That would make sense. That is not specified here. This is LAPAC, and we are looking at C BLAS. See the apple. Yes, okay. A little bit better. C BLAS order should be C or F. And then that is defined as C plus row major, or call major. Where am I at? Let's go up to that one. There we go. Is it row major? I have no idea. C plus studio. We need to link to it. And we want to link to the correct one, which is so we want to have this. And there's a sequential lid blast, and then an OpenMP lid blast. Last time I used it, that OpenMP one was a disappointment. But we'll give it a shot. Okay. We have now something that compiles, and translate setting 78 is illegal. C plus transpose. Should be C plus no trans. Things work much better if you use the correct documentation, I think. For sure. Parameter number 8 had an illegal value. So this is 1, 2, 3, 4, 5, 6, 7, 8. Add an illegal value. Am I using the right one? So 1, 2, 3, 4, 5, 6, 7, 8. That is an array. That should be a pointer. Yeah, and this, so yeah, like there's all these small differences between the different C classes, which is annoying because, you know, it's kind of supposed to be a standardized thing. But the NLC library from NEC is also one of those. When we look at S blast, please. Let's look at the C blast. And I think yeah, I don't think they like give you they don't give you anything special here, but they do tell you the compiling and linking steps. So you want to source those, which I did. So those are there. And then you can have like these 64-bit or MPI ones. And what we will want is FOpenMP for those. And link for C blast, we want LC blast, and then L blast, OpenMP and MP, and you know, like that's pretty much what we want. I think we're using 32-bit ints. No, we're using 64-bit ints, aren't we? default. But if we didn't have any argument to NLC bars, then we're in like 32-bit world. I think that's good. That should give us, double the performance. So we want to stick there. Okay, so what is wrong with my W? Now that can be right. Can that be right? That should be wrong. Exactly. These are already pointers. We don't need addresses to those. Tyler's happy, so that should be good. Tyler's happy. What is wrong with my W? Number 8 had no longer value. 1, 2, 3, 5, 6, 7, 8. So let's see if I can find. Okay, this thing says that our C interface and C class is contained in this. So if we look for C class, then there's no SGMM here. So let's look things up the hard way. So let's go VI opt NECVE lib, if we want NLC, then in 230 we have our includes. That's where our cblast.h is defined. Look for SGMMM. Okay, so orders 1, 2, 3, 4, 5, 6, 7, 8. That sounds about right. Could it be because my alpha is wrong? That could be it. Let me see what. Mention alpha. That's what I care. The Apple one was pretty good. Okay. Alpha, scaling factor of the product basis is A and B. Yeah, it's multiplied by AB. So it should be 1. Pretty much what we want. Oh, man. Let's see. Trade parameter int has an illegal value. Let's check what Google says. SGMM. Wait, did I use? Yeah, I'm using C plus SGMM. Okay, so we want row major. Introducing row major storage. The leading dimensions. Ah, okay. So it's like a dimension thing. Okay, so they are not transposed. So it's D rows and N columns. This has one row and N columns. This has D rows, and one column. If I'm not mistaken, I could be wrong. I'm saying that I got it wrong. So LDC let's give GP4 a try. So these are there. And move this over to T and ask it what. Let's give me a better idea. Okay, this is back, finally. And if I'm not mistaken, sum x. Yeah, never mind. Okay, so I think number 8 is the leading dimension of the second matrix. So I'm saying that the matrix X is the number of rows. So there's n columns, matrix W is in row manager, then fetch B is D, fix the issue. So if W is a DN in matrix row order, then D should be the correct leading dimension. D should be the correct leading dimension. Since I'm using that, it should be 1, so that seems correct. N columns. I see. So it's meaning that okay. I really hate this visual glitch. I have no idea why CSS is so weird. That's the way CSS is. Yeah, the batching is another thing. The vector engine is also really good at batching. Luckily, the code. One of the things I was kind of thinking of looking at as well is in VEDNN. There's a batched. There's a batched version of something in here. And I was thinking of possibly using it. Was it in the intrinsic? Forward. Yeah. And this is where it gets crazy. No, but I'm pretty sure there was a batched GMM in here somewhere. Could be wrong. There's definitely like a batched GMM in one of these things. And we should probably look into that later. Or was it in Frovenus? It might be in Frovenus. I'll check that. Does the VE have its own chip just for job coordination? I don't think so. The VE doesn't really it doesn't have like a huge number of threads like a GPU, so the way you work with it is kind of simple. Now it could be that they're scheduling in their like OpenMP and other implementations might not be great, which is a possibility. But the way to fix that is just, you write different code. So like it runs in the scalar CPU essentially. Well, let's look at that diagram again. So yeah, essentially the entire thing is like this. You have your cores, right? So these are like CPU cores, just like your Intel ones. And then they're connected to their caches and to the HBM. And there's actually 5 of these, but they actually kind of limit it to 8, unless you have the expensive ones. And the scheduling, right, of the instructions is just done in the computer, like in the core, right? The SPU it's not like one thing, like this SPU, VPU, these two things are one of these cores, right? So this is one vector core, this is the other vector core. So it's like done inside. So it gets, in terms of scheduling, this is instruction scheduling, which includes renaming, right? So if one vector is not ready and it can rename it to eliminate things or like do stuff like that, it'll totally do those things. So kind of a lot more traditional in that sense. And there. And needs to be in D. Okay, so it's saying this is wrong. And the number of rows in matrix A and C. Right? Now, this should have D rows. That's the first one. And there are D rows in W. That is correct. Then the number of columns in matrices B and C. Now I have N here, but this is 1. So 1 column here. And therefore this is actually N is 1. Then K is the number of columns in matrix A and the number of rows in matrix B. Columns in matrix A is n. The rows matrix B is n. So this should be n. Okay, scale by 1, and then we have A, and then the size of the first dimension of matrix A. So if you're passing mn, it should be m. This is supposed to be d. So put d there. Then x is our b. And then we should put the m for x, which should be n. Scaling factor for matrix C should be 0, C, and then should be m, which should be d. Okay, so that makes you wonder, because like, wait a second, what is the use case for having to specify just the leading dimension of those? I'm not 100% sure. Count could possibly be 1. That was the thing I was not too sure about. No. Okay. Let's count the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's complaining about B. Okay. Let's do that. No, that's not the correct one, apparently. So our x has, should have n, right? So B, we're passing a matrix B, M, N. The value should be the M. First dimension of matrix B. Which should be, okay, so M is the number of rows in AC. N is the number of columns in BC. K is the number of rows in matrix B. So essentially, LDB should equal K. Right, and MNK, so this is MNK. Right, so this should be N. Let's do this. Twice. Has the leading value. And it's see if there was something. I think it's right. It's the leading dimension of the second matrix, which is x, which you're passing n. But since it is row major, x should be at least as large as the number of rows in x. So this is an n by 1 matrix. Leading dimension should be n. So you're passing the correct dimension for x. That's what I thought too. Should double check the actual dimensions of x. Okay, so we call major order cause issues. Could it be that this is actually in C Blast column order? And that will cause so many other problems. Oh, but it runs. Okay, so that's good. But then my thinking of this is wrong. Okay, so it's running now. So that means it's happy with this. Output is totally wrong. So, I mean, it's wrong because I'm pretty sure it's not in column major. The transposes are A and B. Just because I'm curious. And I'm not sure. I'm no longer sure. I know what. I kind of assume these are in row order. They're in column order. You have to do those things differently. Okay, so yeah, okay, so we get that error. Pretty sure no trends is what we want. But these are wrong. Could it be 1 times D times N? This is N times D. Column major. 1 column, D rows. Then if we look at this again, the number of rows in A and C should be D. Correct. Then N is the number of columns in B and C, which would be 1. Then the number of columns in matrix A and the rows in B should be N. Let's column first. There's. Wait a second. Okay, so this is correct in terms of dimensions, but we know it's wrong. Because the output isn't right. We have row major order. What that means is that it should be the other way around. It should be the other way around. And this should be the other way around. And if that is the case, then rows in A and C rows in A and C would be D, which is correct. Why does this work out the other way around as well? Wait a second. If this is the same, that. And the number of rows in A and C do not match up. And that's what I was complaining about before. So if this was row order, this would be N, and then this would have to have not D, but N. And then this would have to be not N, but D. So therefore that would be N. Number of columns in B and C, which would be 1, and this would be D. Then this and N, so that would be N, that would be 1, and that would be 1. I hate dealing with matrices. D. These are the columns. This should be the M's of C, which is the rows of A and C, right? Rows are first. So that would be N. No. But this one wouldn't be 1, it would be N. Then no, that would have to be D. And this would be N. Looking that way. Okay, we have I. I's are D, first dimension, D. Then we multiply that by N. N is the second dimension. And X is essentially N. Not crazy, right? This is row order stuff, right? Right? X out D, because this is 1, this would be D1. That's D rows and rows. Therefore, this is E times N. Then X should have dimension N. And out should have some dimension E. Right? And if we are in row order, we're not transposing. The first is the number of rows in A and C. Row order. A and C have D. I'm going to have the same thing as we had up here, right? Okay, and then N is the number of columns in B and C. B has 1, C has 1, so that would be 1. And therefore, the only remaining thing is the number of columns in matrix A and the number of rows in matrix B, which is n. That is correct. N goes there. It's scaled by 1. Matrix A is RW, which has D rows. Is the number of K is the number of columns in A and rows in B. Therefore, M is the number of rows in A and C. So therefore, D, which is the number of rows, is there. That's D. Then X has N. Out as D. Yeah, something like that. Because it doesn't like that. It's the same thing here, right? Same, but like I'm thinking of it in column major order. And that confuses me. So I'm not thinking about it in column major. I'm thinking about it in row major order. Let's can just shift these around, right? I'm pretty sure I did that just a little while ago. That would be D, and then this would be N. Oh. And then this would have N. That's like totally wrong. It would have to be D, and that also makes no sense. It wouldn't be 1, which is the only other option. D, N, E. That makes sense in row major order. Okay, that ran. It's wrong. X is N. X out is D. That totally does make sense. We're getting not so good things here. Though the tokens a second are nice, right? Having 150 with that is good, I guess. It's not really that good. I kind of want like 10 times that. Let's do the prog inf real quick. Yeah, our vector length is kind of small. Now, I'm not sure if it's because the model is small. That could totally be a thing. Is it that X should be transposed? Let me check some old code real quick. Not done anything this low level in a long time. Then I have a followed by CPP and Skullnet, MD for J. Thought I had I mean, I'm pretty sure I have it on my blog. Did I have it on my blog? That's so long ago. Okay. Hello, MD for J. I do think you want to have. Oh, hey, Freeman, how's it going? Yeah. Inputs are transposed multiplied by the W. Okay. Yeah, that's right. That's right. So our inputs are the X. And then for SGMM, we are looking at, because I have no memory, B is the input, and therefore trans B should be transposed. I think that will make things work. Okay, so if that is the case, then I think this will start to make more sense. We have N1D. Okay, so if I just transpose, this will not work. X should have 1, and out will have D. What's your problem? What is your problem? X is transposed, right? Or does it ask us without the transpose? Before the transpose, that doesn't make sense. 8 has no meaningful value. 8 is 1, 2, 3, 4, 5, 6, 7, 8. D is not supposed to be D, it's supposed to be N. No. It's row major, it can't be that. Then it can't be 1, right? Because that makes no sense. But it liked it. Why would it like it? Why would it like it? I could also transpose the weights. Transpose the weights. Still have the same NT, but then W would have N, X. We would not transpose. And the rows of N is X. Then D, X out, D rows. It's so confusing. And we're back to where we started essentially. Why does this not work? What is the difference? What is the difference between, let me see, GPT-4 has any insights for us? Should be cool. I don't think it does, but maybe it does. I don't know. Who knows? Let's see. It might be like, oh, these are transposed. You're not supposed to transpose those things. So let's go back to the non-transposed version. This should have E. N1D. Sense. Why would this be N? It's not good with that either. Okay. What did I do before that worked? Okay, so we have D rows, 1 column, and that was the number of columns in A, which would be N, yep, and the rows in X. So that is correct. And the rows, X has N and out has D. So that should work. It doesn't. Updated. Yes. Okay. Anyway, let's see if there's any AI intelligence to be had here. The SGMM does not output alt. Yeah, so we are at up to 150 tokens per second, which is not great. I'm pretty sure with this model, my MacBook Pro gets 200. So I'm kind of really expecting to get like 1,000 or 1,500 or something like that from the vector engine. So we want column major, no trans, D1N1 F WT XN XFD. Actually, let me just ask it directly to translate this. Rewrite this function to use CBLAST. Maybe I should just do that. Like, why try? Rewrite this function to use CBLAST. Oh, okay. So there is a matrix vector one. I didn't know about. I didn't know about that. But that's not. You showed us the S dot. That's not what you mentioned just now because you mentioned SGMP. Okay, so let's give that a quick try. If we can copy. Real quick there. Here. And just the AI blindly. Okay, better. We're at 104, which is definitely more than whatever. Let's try sequential. Yeah, see how that's so weird that it's like, wait a second, you mean it's not faster? Right? Like, how does that even work? We parallelize some things and just get slower. And then if we were to OpenMP this again, and then use allow the use of OpenMP. We're at 105. Okay. So what card am I running on? I am running on I'm running specifically on card 0 right now, which, if I'm not mistaken, is a 20B. So it runs at 1.6 gigahertz. It's 48 gigs of RAM. And yeah, seems to be nice and cool right now. Not working too hard. Now let's look at the proginf real quick. Okay, so we can see our average vector length has gone down, and we're using less vector ops than before. It's like, isn't this supposed to be like the optimized library in NEC? So, but like it could be that this is really optimized, right? So it's skipping calculations that we were doing here that were unnecessary, right? Totally possible. And I could parallel the C+ call. I mean, the idea though is that it's already supposed to be using OpenMP inside, right? We should be at the same, like trying to parallelize the thing that calls this, right? Like going parallel on the layers, which is not good, but in theory, shouldn't help you because matmul, which is using this, which is using the OpenMP versions, should be using all the cores. I can try to check that out. Let's see, VE bin. And there is no source for the NLC libraries. Those are proprietary libraries. We can only see the headers. And there is a command. I can look at the threads. And we can run it. And it kind of ends way too fast. Let me see if I can produce some more tokens, give us a little bit more time. The other thing that we can do is it's nice because you can kind of see things going on while it's being generated. It's probably not so good to printf and fflush in between your things, right? So we can probably fix that. I want our steps to be $256. Can I just take up this? I don't think I can. Let me try it. I can't because it's limited to the config line, which should be 256. Yeah, you can see it's just like spending too much time. Let's move on, because it could be that this model is too small. Totally reasonable. It is a very, very small model. So let's go with let's take out the big guns. So let's use the 7B model. If I'm not mistaken, in my SSD storage, I should have models. Let's check. I have a Llama CPP here, which has some models. Those are Llama CPP models. Now that's another kind of unfortunate kind of thing. The vector engine supports 32 bits and 64 bits, and that's it. So if you try to quantize to 16 bits, or I should say, the vector engine I am using has 32 bits and 64 bits, and that's pretty much it. The new Vector Engine 3.0 supports 16-bit floats in both brain float or IEEE format. But I unfortunately do not have that. And yeah, pretty much one of them, when they were interviewing me about how they can make the vector engine do better for deep learning, I said 16-bit floats for sure. So they helped with that, but I don't have those, and these vector engines are not exactly cheap. So just gonna have to make do with what I have. I unfortunately have many. Okay, so we need a 7B model. And I should have access to it, but I don't. For reasons that I do not understand. I think it's like email reasons or something like that, but I'm pretty sure I've set the things. Like I'm pretty sure I gave them the right email, but I haven't received anything about Llama 2, so I have to get it from not so correct things. Should be this. So pack 2 FP16 into it. I have thought so long and hard about how to do that. But there's nothing I can think of. Like I can think of kind of taking FP16s and saving memory by packing them in, and then doing some quick vector masking to get out the right things. But that doesn't speed things up, and the vector engine is kind of not exactly the fastest card anymore. So my main, I have plenty of RAM because we have 48 gigs. That's a lot of RAM. So, plenty for a 7B model, right? Even in double precision, maybe not in double precision, but we can load these 7B models in 32 bits, and that fits just fine. So I don't need to quantize it to get it to fit in there. But if I'm quantizing it, and any kind of, even though we can support 16-bit things in here or 8-bit things, if you use bytes, that gets executed in the SPU and not the VPU, unfortunately. So nothing can really speed it up. I do kind of wonder if quantizing the 32 bits, similar to how you have 8-bit quantizing, and just kind of using ints for most of this thing might speed things up a little bit, but I kind of doubt it. It's like if it does speed up things, it won't be by much. Okay, so where was I? I think Meta was saying it has published those things and you can get it in a couple of days or something like that, and I never get it. So we just look at that. And I need to access this from my Safari. Okay, and then I have to agree to stuff. Ah, darn, I guess I can't do that. Yeah, we also need to get these batches. So when it comes to Intel, the lack of memory bandwidth, and I mean, I guess it does count to the vector engine as well. But essentially, the output that is showing the average vector length, that's your batch, right? You have cores, and they should be processing 256 things at a time. If you're doing a vector instruction with a vector length of less than 256, it's going to do those calculations up to the vector length, but it doesn't speed up just because your vector length is shorter. Your instruction is going to take a set amount of time. So to maximize performance, you want to have your vector length always be 256. And that is, paramount, essentially. And that's what you want to aim for. So we are seeing that our vector length is not 256, and that's the main problem. Is there a way to make it 256? That's a good question. Let's get rid of these parallel things. And this is the thing that's really weird, right? Like you would think that if you have one vector engine, see that again, you can see here in the threads, if we can do it at the right time. One thread is getting 96. How is it that 8 threads cannot be getting 800? Which is what I expect, right? We should be in the thousands, right? Now if we have 8 times more things. Let's look at the average vector length here. Our average vector length is less. It's at 115, right? It's like, damn. Okay. Yeah, and I also mentioned that there's so Freeman has a good point, right? Like it's not really 256, and that's true. It's at 32, right? So essentially the vector length that you can put in a single instruction is 256. And if you do it that way, then these get pipelined and hide the latency of things if you have enough kind of vector instructions with high, like 256 vector lengths. But they do get processed 32 at a time. So in the cycle, you should only expect 32, but in 4 or 5 cycles, you'll get 256 or something like that. But anyway, so our vector op ratio is higher here, which is good. That means that the OpenMP stuff is adding more overhead than it's really worth. But then the other thing is the vector length is kind of small. Let's peek into a little bit about what's going on in matmols. So when we do our matmol, where's our matmol? Let's print out our sizes. That should slow things down considerably. And it looks like our sizes are, let's put this new line here just to make things a little bit easier to understand. Okay, so our N's are 768 and our D's are 288 in general. And then at the end, there's some 32,000s. So that's bigger than I expected. Okay, so we're not dealing with like super small matrices. Back to the original matmol real quick. Okay, 72, right? So there is some advantage to it. If you look at proginf, we have better vector length usage and more ops, but it's slower, right? It's like, that's weird. We can, let me turn on M parallel real quick, so we can just like see what that looks like. Okay, a little bit faster. If we look at the details, yeah, coordination takes up a lot of our vector stuff. So even though, you know, we are using 8 times more power, coordination is kind of not really worth the overhead in this specific scenario. Let me look at that guide again. Linking. Yeah, isn't it weird? Like, you gotta really have to experiment when it comes to accelerators. These things are kind of very complicated machines, and you know, like communication is not free, and you know, OpenMP might not necessarily be the best. I don't know, like it might not be the best structure for parallelizing when you have 8 cores arranged in this kind of loop. So this is like a token ring type of deal. Like your one vector core can communicate this way and this way and this way, but if this core is communicating this core, that's going to take some time. The explicit timings are not shown anywhere, but yeah, there is this idea of this NUMA node and stuff like that, which gives me an idea of something to try real quick. So let's go. Let's add in the OpenMP. Okay, so now we should compile with OpenMP. And remember this, which I always forget. Okay, so we're at 90 here. And I can do VEOMP num heads equals 4. Okay, and then what I want to try is to pin to one Llama node. And that was proc bind, I think. No. Was it proc bind? I don't think it was proc bind. Or maybe it was. No. OMP proc bind. It was proc bind. What was the... What can I pin it to? Pin to single CPU. Okay, 4 threads. First 2 threads. First socket, the other 2 threads. First cord, second socket. Places is weird. Let's try that. Close. 79. No real difference there. Let's run it with that to see what's going on. That's not going to work for our NEC OpenMP, unfortunately. I guess I don't have it in Llama node. Yeah, so in here I'm setting the num threads to 4. Let's also try the num threads is 2 or something like that. That seems a little bit faster. But it's not. Then if we do num threads 1, it's even slower than the default, which would be 8. We get our 91, which is weird. It's non-trivial. Okay, so let me check out real quick my max function. Back here. Let's use it somewhere. Well, let's see what. Let me just check. I want to see what it says. Okay, so if it hasn't gotten rid of it, and it might have. Where's the argmax? Max was. Float size. Let's config slides. To use it, it's a streamlined max. It's not. It's only fused one loop. Okay, so 44 baseline, 97 with 8 threads. So how big are the matrices? So when I ran it before, they're 768 by 288 in general. And then there's one that's like 32,000, which is the vocab size. So they're small. They're not super big at all. So, well, small relatively, right? Okay, let me see if I can get an F trace. So that's one thing that you can do here. Okay, now we're running an F trace. You can see how much slower it is when you're tracing stuff. And let's give that a second to run. And with F trace, we can kind of see which functions are being used the most, like what's taking up the most time. And then that will give us some more information to work with. And if someone knows where we can get a Llama 2 7B OG, let me know, because I only know where to download the quantized ones, but I need the OG to deploy here. Or otherwise, if any one of you guys have access to that and are able to follow this export meta llama bin, I want to try this because this is a much bigger model, and it's supposed to be pretty slow. And I kind of want to see what a real model looks like. Is there an NV top? Yes, there is like an NV top. I forget what it's called. I'm not sure there's like an NV top. There is a what is the thing that creates the graph? Yeah, that's a good question. I've done it before. It's just I forget what it's called. There's also one of these displays the usage graph. Are okay, so it's that time. Load. Load? I don't think so. Yeah. I've seen it before. Like, it's just a command that I think is from Unix days, but I've never used it, so it doesn't stand out to me. Yeah. Okay, cool. So now we should have an trace.out. Let's get rid of no, that's not what I want. that window. If we F trace, CV NF trace F trace out. What? We can see the outputs of this thing. And we can see that we spend a good amount of time in MapMol, but a ridiculous amount of time in compare. So that's a little surprising. Calling compare quite a lot. So let's look into that. Okay, where is compare used? That doesn't look very vectorizable. Quick sort. I see. So there's other sorting algorithms. The sorting algorithm that works the best, from my knowledge on the vector engine, is a radix sort. The implementation is not trivial, though. And we don't necessarily need to sort. We're looking for the max K. Exactly. Max instructions. Is it going into the weeds if I add the max K code in here? It might. That code. Problem is the code that I have is kind of like approximate, because when you are getting the top K, right? In general, you don't really care if it's really sorted, because once you have like whatever it is, like 256 or like up to 256 top Ks, you can sort those values after the fact. So you don't really need them to be sorted all the time when you're searching through that. And that's how you can get that to be super fast. And it's kind of what we want to do here. I think we can get rid of the sort. Duck sampling is not something I've heard of. Yeah, I haven't heard of that. Don't know what duck sampling is. Sample top P. We have our probabilities. What we want to do sample top P. Then we take random multiplied by the top P and do that. Ooh, BE partial sort. Ooh, look at that. Okay. Oh, I'm gonna have to type it out. Oh, that's so going to be super. Hmm. Hmm. That's a good question. So the vector engine is not really good with functions like this, right? So this function is kind of being called in the SPU. It's being called a lot. And the SPU is kind of slow, and so this is kind of slow. And we're not really taking advantage of the vector engine by having a method like this, or like function like this. And we do have vector compare instructions where you can take one vector to another vector and then produce another vector of 1 minus 1, 1 minus 1. Or maybe not 1 minus 1, but you can have ones and zeros in there. So we can vectorize this compare. So that's one thing we could possibly do. And qsort, like calls stuff. So that's, it's not ideal. And that's why we're spending a lot of time doing it. What we want is this last IDX, right? So we have our probabilities. So this sorts them by the top. We don't care about them sorted. We just want the top n probabilities. Let's do a quick experiment on this last IDX value. Get rid of ftrace. That's another thing. You can see how interesting and useful ftrace is. I need to switch my headphones. or just not use headphones. Let me know if there's like echo, or if you hear the music in the thing. Shouldn't, not talking anyway, so it should be fun. Okay, so let's get rid of that. Let's compile and run again. Okay, I always forget the new line because I program in Java too much. Okay, so this last IDX is always quite small. Last IDX is greater than 256. Print it. It's never greater than 256. Okay, so what is the max? We have our max IDX. IDX is time break if last IDX is greater than max. Max. X. Let's just move this here. So what I'm thinking of doing, okay, so our max in this particular model is 97. So yeah, essentially, what I'm thinking is, you can imagine we have an array, right, of 256 things, and then we have our values. I don't like that this is blue, but there, I can't change it, seriously? It's white. Okay, and then make this be a line. Yeah, sure. Okay, so the idea is, right now we're like sorting this entire thing, which is kind of big. Actually, how big is this? We want, n. So every time we print that, let's print the last IDX D, N, D, N. It's only 32,000. So we're sorting 32,000 things to take the first 100 at most, right? Instead, we can take our 256 array, put the first 256 things in it, and then slide it by 256 and compare anything bigger than something in here, and go here, do the same thing, and go here. That way, you're only doing it like 2 or 3 times. Now, this does have a failure mode. We can see how that works, but if you happen to have, a probability that's like kind of high here, and then a probability that's kind of high here, and those are both in the same slot, that's it's and yeah, this is not going to work. So it's approximate, but it's really damn fast. And I think it won't matter, but we could, I think, fix that by doing this multiple times, essentially. So let's implement that. That should be like crazy fast, I guess. Let's get rid of this experiment of the max IDX real quick. And this is also not so great for performance, as you can imagine. Like having break in the code, it's like, nope, don't want that. Okay, so let's change this old sample top P, create a new one. We have our probabilities P. So let's do an assert that n is less than 256 because that is the max we will support. Index. Top P. We don't know what it is. I don't know what it is, but if we just limit ourselves to 256, I think that'll be fine. Smallest samples from the smallest set of tokens that exceed probability top P. Right. So then the idea is we truncate the list where we have now exceeded top P. Abilities. So get my C line code here because it's not the same, but I'll like reference it. Let's see. No, that's not my code. Okay, fine. Well, let's just make it from scratch. Doable. Okay, so what we want to do first is get the top 256 probabilities and find create a cumulative sum vector. Find the index. They're not sorted. So you can have 256 things. You can sort that and then go through the window again. Essentially the problem is we're doing it exactly this way, which we don't necessarily have to, I don't think. Like it'd be a different type of sampling. So here we're looking at, we take the top probabilities, and then once it's reached a certain threshold, now we ignore the rest. We know that in this particular benchmark, that threshold is 96. It's usually less. So you can argue like, okay, fine. What if it's just 256? We have 256 things, and you find what it's more, but you'll still be sampling it based off of the probability, right? So I think I'll be fine. But anyway, so let's first get the initial. Let's do this part. So first, I'll create my float array P. I want to call that. We want to call it window 256. And for int I is equal to 0, I is less than 256, plus plus. We will set window I equal to prob index I. So now we have the first things in there, and then maybe let's put it's 32,000, so int, let's put chunks equal to n divided by 256. And for int chunk equals 1, chunks are, a chunk is less than the total chunks plus. Then what we want to do, trying to remember that code, but I think we can have a for int I 0 I less than 256 plus plus, and if window I is less than prob index times 256 times the current chunk plus I. So if the thing in that particular window is less than that one, then we will set window I is to prob index 256 times chunk plus I. Okay, then the window has now gone through the things, and the probabilistically top 256 things are in there in some order, right? Some like stochastic order of some sort. We don't know what it is. Now, I think we can just give this a shot. Prob index I. Probabilities I. Right, I don't want prob index, whatever, I want probabilities. Okay, and I will also want the locations of the probabilities. Wait, is this an out? Yes, it is an out. It is a non-ideal struct. Yeah, okay, so let's, so it's a struct that has two different things, right? And that's not really good for vectorization, right? It's like the thinking of you want like a data oriented thing, so you just want an array of values and an array of probabilities. So so how long is the thing you try to sample the max from? 32,000. And we are returning. Okay, so we're returning this prob index, so we don't really care about prob index per se. We initialize it, right? And we sort it. We're doing something, we're returning, the index of the thing that has the most probability, right? There can be many things with similar probabilities. So like one option is we have these probabilities and they're pretty unique. So we can just have the probability and then find the index afterwards and return that. That's kind of dumb. Still could be pretty fast. Anyway, so let's put an int idx's 256. Maybe x's of I equal to 256 times chunk plus I. And then idx's I is equal to I. I have to look at the compiler output for this, but I think that could be it. So if this happens, then we set that value and then we put that in there. So it's like a max kind of thing. So now we have these 256 probabilities, right? We need to sort them. Again, 256 things is not super crazy, but I'm going to try. Let's see what it looks like if we don't sort them. And we don't truncate them. Because we've already kind of truncated to 256. Here, the cumulative probability element-wise max over multiples of 256. Yeah, that's the thing. It's more precise that way. There's also more work. Okay. Anyway, so we have our truncated list, which is our window, right? So we're going to take some random floating point, multiply it by the cumulative probability. And then we have our CDF, which I'm not sure what it stands for. We have distribution thing. We add that R. So we have some random floating point, which is some subset of the cumulative probability. And then we wait until we have one in there. Index size index compare. Okay. So I do think we need to sort the 256, like the window. Yeah, let's kind of keep it. Sorting 256 things will be much faster than sorting 2000. We don't want to use qsort because it's 256. What we want, so Paul is here. So yeah, so what I'm doing right now is we ran ftrace on llama.c or llama2.c and found that this compare function takes up the most time because it is comparing the probabilities for this sampling, this top P sampling function. Now, since we have done some interesting things with top K and Vecto, I'm kind of applying the same kind of principles here, but I can't find that code. So I have to kind of create it from scratch, which is kind of unfortunate. Right now that top K is here, right? And I looked at that just. Yeah, this isn't my code. So there's no point in looking. Okay, so we don't need quicksort. We just have 256 things, right? So for 0 on is less than 256, plus plus. I get it to generate the max instruction. The top K and top K is the same as the top is the same as the P and the top P. Essentially, this is like the number of things. So in a vector search, the top K is the top, things that you're interested in. And here our top was less than 96 in every case. And yeah, in the vector code, we do have like the precise top K that we have. Yeah, and that's also another thing. So Q sort is not necessarily super fast. There's definitely faster sorting algorithms. Remember, Karpathy's goal with this code is something that's easy to understand, not something that's like high performance. So it's fine, right? Like, I'm not saying that he's doing things wrong. It's perfectly fine. Okay, anyway, so we have our probabilities in the window and these IDs, and I'm going to create another int for DIRD 256. Do we need the probabilities? We do need the probabilities. Okay. So let's create a temporary copy of window, like window 256, or int I plus 0, I less than 256, I plus plus, and window I, or window 2, I is equal to window I. Okay. And then we have our ordered indices. But yeah, like the thing that we used in Vecto was just like calling the max and then removing it and doing that. And that's essentially what I'm going to do here. The only thing is I have this window, like this probabilistic kind of maxing thing, which is super fast because we're kind of going in chunks. But anyway, okay, so we have our copy of the window. What we're going to do is find the max in window 2 and then set that value plus int max idx at 0, right? And for int I equals 0, I less than 256, I plus plus, we're going to go find the okay, well, let's do this 256 times. Okay, plus plus. So find the max IDX if window 2 K is greater than window max IDX, and max IDX is equal to J, and window 2, set that there. Okay, now once we have that, we set, what is RRSTPT? Anyway, let me finish this because I kind of want to see what it looks like. Okay, so we have our max IDX. This is the highest in the entire thing. So ordered I is equal to max IDX, and then window 2 max IDX. Now let's make that equal to 0 or negative infinity. Let's try 0. And then I'll do the second max and third max, right? Pretty simple. Now our ordered indices are there, and we can calculate this properly. By ordered index in window, because window 2 essentially becomes just all zeros. So we have that. Then if we're greater than top P, we break. And then here, we do window ordered I then the index that we want to return is the IDXs ordered I. And if not, then we return the index, the last RDX, which is IDXs of ordered last IDX. Let's see what kind of craziness I wrote. We have 571 should have a semicolon here. Good. And forgot to uncomment this thing. And here too. IDXs. Okay. So if you didn't notice, that was really fucking fast before it crashed. So that's good. That's a good sign. But we crashed somewhere. Yeah, once upon a time, there was a little boy named Timmy, and yeah, so usually it's like it starts with once upon a time there was, and then a lazy cat named Mittens and stuff like that. So that's, you know, kind of makes sense. Seems good. I run over the end of the array. So let's look at that. Okay, leftover in the window, and I think, yeah, it's something along those lines. These indexes. Yes, that's true. So we have 32,000 divided by 256. And in this case, it should be the same, but could be possibly wrong. 2 is that. Let's print out what we're returning. Printf. I've never taken a look at it. Well, I'm pretty sure I've taken a look at the core dump. Okay, well, that time I didn't core dump, and we got 420. That must be a sign that this is a half-baked implementation for sure. So 420 is 4 times faster, and that's not using. Well, I guess we are kind of using the parallel stuff. Kind of see. Is this, how consistent is this? Yeah, so yeah, inconsistent is exactly what it is. But the outputs are kind of okay, right? Finally, Tim decided to eat his lunch fast, you know, so we're not too far off, but something is not right. Why small segmentation font? So you've put it small. And just check to see if it's like a rounding error type thing. One. Cool. Yeah, now you don't fail. Okay, thanks. If instead of this I returned 0, that's a fail. So it's not necessarily this line of code, but it does seem that this line of code almost never happens. Let's check that. But the IDXs of ordered of I and I seg fault. So I return 4802, which seems to be big, and then I seg fault. What? 4802, which is not like, if it returned like 10 million or something like that, I mean, yeah, totally screwed there, but it's 4802, which is less than 32,000. Okay, let's print I2. So our seg fault. Yeah, it's interesting how, in general, it's returning 0, right? It's like a whole lot of, 65,000 sorts to just always return 0. Kind of seems like you could probably optimize that. You'd probably like merge the two. So like we find the max, and then if the max is higher than the top P, then we return 0. But if it is not yet the top P, right? If that max is higher than top P, then last index is 0, and then we do whatever that was, and no, we're not returning 0 because we're always returning 1, so it's not necessarily going to be 0, or like 1 here, as in we're kind of not returning from this branch, we're returning inside of here. So something, order 1, IDXs, and order X and IDXs are both 256. That's true, I probably flush. Telling my son that he needs to learn to flush. What did I have to flush? I have forgotten how to flush standard out. Okay. It's a weird seg fault. Weird seg fault. And chunks. One sec. Let me see. Am I seg faulting here? I have to be. Aha, so is here. So where am I going wrong? Chunks, n, which should be the number of probabilities, right? That's a good idea. And it's always 32,000 because it's the vocabulary size. So there. In line 539 might be out of bounds. In theory, yes. But if we're always getting 32,000, then no. Right, because essentially it would be 32,000 divided by 256, which would be 125. So then we're at chunk 1. This is another thing that kind of sucks. Usually I would just hit a debugger and then find where the thing. 256, right? 32,000 divided by 256 is 125. So 125. 124 is the last chunk. That's fine. Need like a Red Bull or something like that, kind of too tired to be thinking. This should also be fine. Let me just check where I'm at. I want to see which for loop it's crashing on. That would be very useful to know. And then that would be 6. I do wish it was easier to have a debugger. Oh man. And you can use GDB for it. It's like not necessarily a problem. It's just that I have seen GBD really mess up the server, and you have to restart it. And this is the server that we're using, so I don't want to do that. It does seem here that we are faulting on here. Okay. So yeah, I think in general, when it comes to GDB and just debugging stuff, it's probably okay. But I have traumatic experiences with GDB on the vector engine, so try to avoid it unless it's a problem. Okay, window ordered by, and yes, that makes sense, because ordered is 256. We're going up to n, and there can be a case where, I mean, we checked that and it really shouldn't. whatever. Okay. I'm not sure why that happens, but whatever. We'll just roll with it. 256 should be fine. When would it go over 256 if when we checked it just now it was always less than 96? Could be I'm doing things wrong. Totally possible. It is 2 a.m. after all. But right now we're racers. We want to see how fast we can go. Screw correctness. Okay. 4. Good. Let's get rid of these prints. I like the way that looks. Let's also parallelize everything else that it can parallelize. 440. I think it was faster before. Nah, it's kind of like in margin of error. Okay, let's also look at the prog inf. Okay, so now our average vector length is about the same, but our vector op ratio is 83. Let's f trace this and see where we're at. Is what on GitHub? Okay, so now we're at map mul being number 1, where we're at what we want, right, essentially. Let's also try this without parallelization at all. Less sequential. Okay, so without any parallelization, we are seeing a average vector length of about the same, but 97% of our operations are vectors, so that's good. Kind of really wondering about why our vector length is so small. Yes, so yeah, this is not on GitHub, but I'll fork it and push it pretty soon. Okay, so that's cool. Paul, do you happen to have the original Llama 2? Because this can convert them and we can run a real model, which I'm interested to see how fast it goes. Probably not very fast, right? Like it says, you know, this guy, when he uses it on his own machine with 96 threads, he gets 30 seconds per token, which is not ideal, I'm sure, but I'm interested. Okay, let me do an ftrace with in sequential mode. And it's weird how you can, like with one core, achieve, you know, you go 8 more cores and achieve only 2x speed up. Is okay. That's kind of short, but out. And we are mostly inside of transformer. And that makes no sense. And that's a good point. So in the VE, if you have threads, the threads will be in different cores. So when I say threads, I mean cores. That's a good point. Transformer has inlined absolutely everything. So when we look at the F trace, we're kind of like everything's in transformer because we've inlined everything. Now let's get rid of these again. There we go. Okay. So 71% of the time is in matmul. Okay, and matmul is pretty simple. Let's use this matmul. And return, get rid of this, we don't need it. Hello. Let me leave that there. We might want to use that later. Okay, now let's actually use the stuff that we said we're going to use. And that broke everything. Wow. It's very fast though. Very broken, but very fast. Yeah, and that's true. If you notice, Paul makes a good point. If you look at sample top P, you know, that kind of code is essentially all sorts of coolness. Yeah, BLD, we're at average vector length 256, of course, because we're using it. But the vector op ratio is 27%. That could possibly be better. But matmul is pretty good. Let's try this. No, I do wrong. Yes, that's wrong. Let's not do that. This one, which is the correct one. Yes, let's use the correct one. That will make our life easier. Okay, that looks pretty good. We're at 600 tokens now. Now let's get rid of ftrace. Okay. And let's look at the ftrace though. Yeah, average vector length 125, definitely better than before. Okay, so let's get rid of that. Let's bring back the inlining. Okay, 639, 666. Okay, game over now. Let's try OpenMP. $1,300. Now we're at where we're supposed to be. This is what it's supposed to look like. 1,300 tokens per second on all 8 cores. Cool. Much faster than what we started with, which was like 60 or something like that. And yeah, essentially what I showed here was like, that's how you do things, right? Like you try some stuff. Once it's compiling, then you ftrace it, see where it's taking the time, and figure out how to not do stupid stuff, which would like using qsort on 32,000 things, of which you're only returning like it's, and even now we're like, like if you saw, we're always almost returning 0, 1, 2, or 3 essentially. Like that's mainly what we're doing, but we're doing this 65,000 times. So we could probably get rid of that as well, by merging it with this, and then probably get even more tokens per second. And yeah, I do want to try it on the bigger models, but the problem is can't. So yeah, what's my email here? Yeah, I think it's the same thing. Yeah, everything. I have no idea how to get it. Where can I download the weights? Try this hacked Llama. There's this random bit torrent. This is also old, I think, right? It's like March 7th. I'm also like still waiting. So I've been able to play around with Llama using, the quantized things that people have outputted. No, what do you mean the 110M model? Which model is that? The Llama 2 110 or this thing's 110? This one? Yeah, I guess I'm running this one. And then there's 42. And then there's this 110. So the 110 should be equivalent to GPT-1 in size. So yeah, I guess let's try that. So this is something I can download. Yes. Let's get it out. This address. Okay, and now if I run that with storage 110, we're at 400 tokens per second on the bigger model. Pretty good. Reasonable. And yeah, God, I wish I had Llama 2.7b bin. Has nobody put that somewhere? There's people with GGML things on Hugging Face. Does the bloke publish the originals? The bloke is great. So he has these Lauras. But does he have the originals? Q. That's 70B. They're not going to be doing that one, I'm pretty sure. Sort by most downloads. Wow, that's a lot of downloads. So what we got? ChatGPT, uncensored. I gotta try the uncensored ones. Llama DL. And I mean, I need to try the uncensored ones in for the agent stuff. Ooh, are these the originals? Llama 2 7B FP16. PyTorch. Will that work? Model 7B. Might work. What does this use policy say? Is there an easy way to download this with a command line? Oh yeah, let me push the code to GitHub real quick. So let's go here in fork this. Specify Llama 2C. Okay. Let's remote add line. That's I'll branch my own right now. And hit that'll be M. Okay, git status. Let's add and see. I don't want to add the binary. Thank you very much. Add compile.sh. Okay. There we go. So now over here in the VE Llama 2C, if you go to the VE optimizations branch, you'll see all the code here. So that should work. And if this, depending on how good 7B runs, we might have like a little server of this running for Technologic. So we'll kind of see there. Anyway, let's get back to Actually, one interesting thing when thinking about whether we should detect the zeros early and do that, that may or may not be faster, because since the vector engine doesn't really like doing branches, right? And same thing with GPUs, essentially, right? So things that it could turn out that doing, something 256 times, right? Or that's what it seems like into the loop. It just becomes one instruction, but there are no branches, and so that kind of works out well. So what I'm thinking is we don't need to do things 256 times, right? Like, we can find the max, do the cumulative thing, and if we're still under, then we do the max again, and then we add that to, so we add to the cumulative every time we have a max until we have that, and then we do the sampling from there. That should definitely be more faster and stuff. Yeah, it's the VE can find the max and very fast in a vector. So you don't have 256 compares. It's one instruction to find the max. And it also, if you look at the max instruction, it will say which element is the max and how much was it, and you can do max or min mode. So it's pretty good. Anyway, I would really like to download this. Right. Makes sense. Let's 3 10 VM. Let me see if I can use the Hugging Face tools to download stuff. Okay. So let's activate. On that, install. There's the hub library. Is that a command line, or is it just a library? Okay. Do authentication off screen real quick. Settings, tokens. How do I download? Download files from the hub. Who am I? Okay, cool. Repo. Game base download CLI. That's what I want to do. Is there no good way of doing that? I see. Okay, I do have a. Okay, it's not as bad as I thought it was going to be. Okay, cool. So let's go to that out folder. No, we go make. Files here. Want to clone repository. Do you have LFS installed on that? Do I need to upload my SSH key to Hugging Face to clone public stuff? I guess so. Let's do that. Key. I clone this using Git. That works better. Okay, so that may take a while though. But it is kind of cool that it works, and we got it to the performance that I was kind of hoping for. Now, for comparison, let's kind of do an experiment. So my Mac gets 190, but that's cool. Okay, make the README mentioned fast version. So what was the fast version? Make run fast. I think you can do better than that. do O fast, F fast math, run.clm 139. And then if I do f open mp, why can't I use OpenMP? It makes no sense. I've done plenty of OpenMP stuff. Yeah, it's not exactly super clean. L. Nope. Back. Probably do that before. Did it stop working? So when? OpenMP with back. What? They got rid of OpenMP in Mac. Can't be right. Let's see, F open MP. It's this GCC that I have. Good work. Okay. Now let's run and look at the activity monitor while it's running. At 140, right? So using OpenMP and all that stuff, only get 140 on Intel. And it's probably all like quicksort madness. So, you know, that may or may not be fair. Let's see, what is the status of that? Still cloning. Ooh, also, before I get too far into that, I should probably stop that. I should probably stop that. Let's see. The reason why is the home directory never has all that much space, and I don't want to get over 90%. So ideally, I do that in the SSD. Oh, cool. Thanks. Are you doing it in this machine or on your own machine? Oh, okay. Now make sure you put it in the models folder here. We really don't want to get any partition over 90%, or we'll have issues. Okay, that's cool. Okay. So there. Okay, doing the converting. Oh, what do you mean that you're on your own? What do you mean? It does seem it's going to take like 10 minutes to do the Llama conversion. So wait. We can maybe look at this optimizing thing. Oh, it's already done? I thought it would take more time than that. Is that the right size? Oh, 26 gigs. I guess it is. Oh, okay, then let's give that a shot. Okay, so we'll do run, and instead of out stories, do starting 2. So what is that ASL RT thing? I haven't heard of that one before. That is not bad. That is not bad at all. That shit's like GGML. Hold on a sec. So let me show you. So here is GitHub Llama CPP, right? And if I do this, right? So this is my Mac. Whoa. Whoa. Oh, okay. Yeah, I was being dumb. Anyway, that's just a public key, so that's fine. Whatever. Let's go. Let's something from Technologic. And yeah, let's just ask this thing to do something. Yeah. Yeah, so you can kind of see the speed. It's like, it's okay, right? Like it's usable, but it's kind of slow. And if I were to do, look and compare it here, it'll take some time to load, and then once it's loaded, that's like way faster. Now, why in the world it's talking about Jesus? I'm not sure. Now, it could be that this model is maybe not the real thing. Who knows? But that is kind of cool. Was there a way to get a prompt in here so I can kind of compare it apple to apples? Hi. Yeah, cool. Okay, I works. So if I were to do the same thing here, let's do this kind of prompt. What's wrong with this prompt? Still going. Yeah, 5 tokens per second versus 20 something. Something's not right. I think there's some slight differences between these two models. Or it could be that our sampling is not great, which is totally real. What model am I running locally? Locally, I'm running this Llama 2 7B chat. Which you can get from the bloke. And that seems pretty good. This doesn't seem so great. Oh, the model that I have isn't the chat version. I see. Okay, so that one makes kind of a big difference. So this instruction stuff doesn't make any sense to it. That prompt is useless. But if I just do something like that, it should spit out something, possibly. But that's nice and fast. I think we'll have some, and it could be even faster because we're doing stuff with row ordered stuff, and that's kind of dumb. Let's look at the proginf and see what we're doing here. Show me how to do that. Yeah, like if we start doing things in columns, like if we transpose the weights and have everything working column oriented, that should be much faster than even this. And then, yeah, our average vector length is 246. Now, now we're cooking with gas. It's about as good as it's going to get. Now, any other speed ups is not from the vector engine, but just like not doing unnecessary work, which this, this kind of is unnecessary work. So yeah, like the vector engine just loves working in Fortran order. The predictor will work better, like the transfer prediction works better, and everything. That's why like just using a Fortran version of some C code is like super fast most of the time. Like it just works. So if we were able to change this code to be column oriented, that would be much faster. Okay, so that's that. Now this cumulative okay, so I think we can optimize this a bit more. I think we had max, right? Input size. We return the max from that. We'll get the index though. And then let's close that. Set IDX to IDX and do that. Okay, so now we have this max function that we should be able to use. Okay, so if we look at this, 90, maybe not 90%, but some percentage, big percent of this, the top thing, has a cumulative probability bigger than the top P. So this last and break we can change. Because yeah, so if I is less than equals the last index, I see. Okay, so it'll be like this is at 0, then this starts at 0, and then we return the thing. So the idea is can we do that similar thing but without sorting the 256 things? So this can be we have a float C prob equal to 0.0f. So in the case of 0, yeah, just returning that is fine. But if it isn't, kind of have to build the same thing. Or we turn it into like a greedy algorithm. And yeah, the greedy algorithm is going to be like faster, right? So what happens if we do that? I'm kind of intrigued now. So let's give it a shot and see how bad it gets. So if instead of doing this sorting business, and this window 2 business, that, okay, now we have all of our kind of maxied out chunks. And we had max, where we take our window 256 and a reference to the max IDX, and we'll have a float max prob. Okay, and then if you want to return that max IDX, right? Yeah, so we return IDX's max IDX. This should work as well, just not as good. If I could remember to have semicolons. Oh. Would help if that was a unique name, right? Oh. Okay, cool. So that is good-ish, I guess. Good this way. Do you ever use the float top P? What is float top P? So if I'm not mistaken, the top P thing, yeah, still pretty good. So top P is essentially used here. So you have a sorted list of probabilities, and you have some sort of yeah, I'm not 100% sure, but essentially it's like a cutoff point. So you're going to take the first, second, third, and then when you add those three things up, if they exceed the top P, then you ignore everything else. And what that does is that because you're sampling from the distribution of all 32,000 possible words, right? And it's like rolling the dice. Sometimes you'll roll a 1 or something like that. So similarly in the samples, you might go way out of what's normal. And when you go way out of spec, then your outputs are going to get a little weird. So by truncating them to a top P, right, there's like some kind of subset of all possible things, and you're only really interested in the kind of probabilistic subset. Then you can change that top P in the app to kind of make, if you want to keep things very crazy, then you have a really big top P. And if you want to keep things tight, then you have a small top P. Yeah, exactly. So it's like in top K, you say, I want 10, but in top P, you say, I want, 0.1 or something like that. And then when you sort all the words that are possible, you're going to cut off the list of things once the probability of the top things reaches 0.1 or 0.5 or something like that. If you set top P to 1, then it will consider everything. But if you put it down to like 0.5, in general, like it will only have like half of the things. Why do they sort it all? They sort because, let me do trace on here. Why do they sort? They sort because they don't want, so if you have like the unsorted list, you might have a bunch of 0.01s or something like that, and you don't want those. You have 32,000 things, right? And let's say that everything has a non-zero probability. You don't want to cut off, things before you get to the most probable words. So by sorting, you're now looking at the most probable words first. And if that first word is already above your top P, then that's the word you use. But if you have multiple possible words, which is always the case when you have like things like names, right? If the next word in the sentence is a name, then there's going to be a bunch of names that are possible, right? So you don't want the other things to kind of interfere. It's like you want the names, and so you're going to take the top 0.5% of names or something like that. Yeah. Okay, so let's compile with ftrace. And then run this. And since it's almost 3 o'clock, I think I'll leave it here after I run that. But this is pretty good. And like the output looks perfectly fine. I mean, it doesn't really look that great because I'm like greedily doing stuff. But look at that. Oh, right, I have everything inlined. Let's get rid of the inlining. And so go to sequential. Llama. Are you converting the 13B normal model or the chat model? Because I kind of want to see the chat model. That would be the most useful one, I think. I see. Yeah, I think we should try to get the Llama models, like go to the Hugging Face thing and then go to the Facebook thing and make sure that we signed up correctly, because that can be a problem. We are stuck without being able to access it. Okay, cool. So here we can see 81% of the time is in matmul. Our up ratio is maxed out. And next is transformer, 10% of the time. And up ratio is pretty good, but the vector length isn't so great. And yeah, sample top P is now, negligible in terms of the time taken. The vector length is perfectly fine. Back up ratio is ideal. So nothing much we can really do there. But this is the greedy decoding, right? So yeah, that's going to be faster because it's kind of dumb and it makes worse output. So it's not necessarily worth doing it this way. But it's kind of cool that doing this 65,000 times is essentially nothing. It looks like 65,000 times, but it's actually not. It's just 200. It's like looping 256 times. Not ideal always, but like not terrible, right? Like, yeah, you can do it. It's not a big deal. And saving, doing it less often is probably better. But it's not going to like super change the world in terms of the performance. And yeah, I'm happy to see a pull request for non-cheating versions of this. It's interesting. It's like this kind of taking only the X number of things and making sure you have exactly the right, exactly the top P, makes things a little bit like a lot slower. And then the way that I'm doing it here with the window is probabilistically okay, but not exact. And that does kind of change things a little bit, but it is quite fast. So, depending on the application, you can do it this way. And I think if you do it if you were to do it with, if you took probabilities and you were able to easily work them backwards and then just do the window twice and then merge the two windows, then that's even, the probability of collisions is even, it's like halved or something like that, or possibly more. But you never know. It's still a probabilistic kind of maxing operation. Let's go back to non-greediness and try out the 13B model. Exactly, you don't want to do that with ftrace installed. Okay, so let's add these. Okay, so everything is nice and inlined and optimized. Fast math is on. Okay, so let's do 13B. I'm not sure if we'll fit that in memory though. SSD models, SSD temp. Let's see how that goes. And then once this runs, I think we'll end the live stream there. So this is pretty good. We started with very, very slow code, ended up with some very, very fast code, and looks like it's printing out the right thing. So that's pretty good. And yeah, I would love to kind of offer Llama 2 as a service, particularly because I spend a lot of money on GPT-4 with the stuff I do with agents, because they like to talk to each other and talk to themselves and do a lot of thinking. And yeah, even though they're not that useful yet, they're costing a lot of money. So having a local model like Llama 2, if it is able to do some of the reasoning tasks, then that would be good. And perhaps we can experiment with multi-models, so having the bulk of the work being done by Llama 2, but perhaps the frontal lobe stuff being done by GPT-4. That would be a kind of cool agent thing to be done. But anyway, this may not work. Yeah, mmap failed. So yeah, 13B is too big to run on the vector engine because we have 13, billion parameters, each one becoming a 4-byte floating point number. Means that we need 52 gigabytes to load it into memory. We don't have 56 gigabytes, we have 48, so that doesn't work unless we're able to get 16-bit floats. So if we had a VE3 running, we'd be able to do that, but we currently do not. So we'll just have to do with 7. Yeah, the VE is satisfying when it works, I guess. Like it's nice that programming it is kind of easy in a sense, right? Like it makes sense. You don't have to go like crazy when it comes to like GPU programming, for example. So yeah. Anyway, so it is 3 a.m. now. So thanks everyone for hanging out with me. And I will be doing a stream on Thursday morning Japan time. So not ideal for everyone, but that's where we'll do like high level stuff. So that's where I'm going to be talking more about agents and things like that, things that use these LLMs. And I want to do it in a more America friendly time zone to see if we can get more viewers and stuff like that. But anyway, that's all for today, and I'll see you guys on Thursday. And if you want more low level stuff, we'll be back same time next week for low level things. I'm not sure what we'll do next, but it might be related to this. Anyway, so that's all, and I'll see you guys next time.